The solar system, our home, vast, majestic, and peaceful. Think again. Once there was nothing here but a huge thin cloud of gas. How did we get from this to this?
When we look out there, we're really looking for our own origins, what happened to us.
Piecing together our system's history suggests a wildly chaotic birth.
It's almost like a planetary pinball game.
These are exquisitely violent events.
It's the ultimate survival story. The formation of our solar system. Throughout history, the heavens have inspired awe and wonder in human observers. Our ancestors watched the skies with amazement, imagining the power of the bright objects that we now call planets.
The fact is that for as long as there have been people, we've looked at the sky, we've looked at what we see there, we've asked the question, what's the connection between that and us?
The ancients erected standing stones, temples, and pyramids from which to predict cosmic events and to worship the gods in the sky. But the first telescopes revealed a universe unlike anything we could have imagined. We began to see what was really out there. Not gods, but planets, stars, immense clouds of gas. In 1755, German scientist and philosopher Immanuel Kant turned his attention to these huge clouds, or nebulae, and in the process came up with one of the first modern theories of how the solar system formed.
All of these beautiful clouds in interstellar space have turned out to be very important. It's where stars are born, it's where planets form.
Kant's key idea was that nebulae could collapse in and condense into planets and stars. It's known as the nebula theory. 250 years later, Kant's theories still help to explain the birth of our solar system. Today, new observations are revealing how the sun, planets, and moons of our solar system took shape. Scientists like Professor Jeff Hester are solving many of the long-standing mysteries of the formation process.
We now have answers to questions that people have asked themselves for as long as there have been people. And it changes the way that we think about ourselves.
Dr. Michelle Thaler is an astronomer working with NASA's Spitzer Space Telescope. It's the fourth and last satellite of NASA's Great Observatory program, and it gives scientists a totally new view of the universe.
What's happening now in astronomy is we're finally seeing the universe as it really is, not just as humans perceive it.
One way to establish how our solar system forms is to watch other distant systems take shape. But if Kant was right and new solar systems form deep within clouds of interstellar gas, we might never see this happening.
Our own senses, what the human eye can see, turns out not to be the whole story. There's so much more out there that the humans just don't have the capability to see naturally.
Objects emit infrared radiation. Infrared has a longer wavelength than visible light, so is not scattered by dust. Conventional telescopes that use visible light cannot see inside a dusty nebula, but infrared sensors on board Spitzer can. The same principle is used by firefighters.
This room is completely full of smoke. There is no way that you can see with your eyes or with a regular camera what's going on inside. So fire departments use infrared cameras to be able to see people inside a smoke-filled room and actually see the heat of a person's body. This is exactly how Spitzer works. Spitzer actually looks through these giant clouds of smoke and dust to see planets inside, just like these guys can find the people. Visible light is completely blocked by things like smoke and dust, but infrared light is a longer wavelength, and actually it's just sort of a happy coincidence for us that nothing stops it in the chemistry of smoke and dust. I think you really get a sense now that we're able to see where we've never seen before using the Spitzer Space Telescope.
A camera in a smoke-filled room is one thing. A telescope in outer space is quite another. On the ground in 2003, Balla and her colleagues wait anxiously for Spitzer's first data. At stake is a unique view of the origins of our own solar system.
Literally, no one had ever seen what the universe looks like in that type of light. So at first we were amazed at the beauty. I did not expect Spitzer's images to be as compelling visually to me as they turned out to be. They are beautiful.
But these are not just pretty images. Crucially, by observing distant worlds as they form, we also learn more about the birth of our own solar system.
One of the privileges of observing star and planet formation is that you're effectively looking back in time. You're looking at what we must have gone through billions of years ago.
What this glimpse back in time reveals is a snapshot of the earlier stages of solar system formation. This is our best ever view inside our nebula's collapse.
We've actually been able to observe with Spitzer the moment where the dust begins to collect together and then get warm, and then finally, young stars emerge.
So it turns out Kant's 250-year-old theory is essentially correct. Our own nebula began its collapse 4.6 billion years ago. It's likely that the nebula had slowly been spinning in space ever since its formation, but as its material collapsed, it began to spin much faster. This is down to the law of physics known as conservation of angular momentum. As the nebula contracts, the same amount of energy is now concentrated in a smaller space. To keep the same momentum, rotation speed must increase. As our nebula began to collapse under its own gravity and spin faster, a dense clump of matter formed in the center. It's called a protostar. At first, its heat was due to friction. But when the clump reached 10 million degrees Celsius, nuclear fusion kicked in. 4.5 billion years ago, our star was born. Hydrogen atoms fuse together to form helium, and in the process release photons. It's the first light made by our sun, and it will keep on shining for 4 billion years. A vast nuclear furnace nearly 1 million miles across. From a distance, this process seems almost peaceful, with the sun's power gently radiating out into the early solar system.
There was all sorts of activity going on. Things were changing rapidly, violence, explosions, intense radiation. We had a pretty spectacular origin, I think.
Recent research suggests the solar system's birth was far from peaceful. Our sun may in fact have been born out of one of the most violent events in the cosmos, the explosive death of another star. And even before that, it seems there was an explosion so huge that it created an entire universe, the Big Bang. No one knows what caused it, but we think that the Bang created space, time, and all the matter in the universe. Yet for astrophysicists such as Professor Stan Worsley, there's a puzzle. The Big Bang produced almost none of the 88 naturally occurring chemical elements.
When we look around, we don't just see hydrogen and helium. We see planets and people, and we're made out of carbon and oxygen, and planets are made out of iron and silicon. And that didn't all come from the Big Bang. It had to come from somewhere else.
Here on Earth, we have learned how to create new elements for ourselves, nuclear technology. The same thing happens inside stars. Hydrogen and helium from the Big Bang fuse to form heavier elements. And if the star's big enough, at the end of its life, it does something spectacular. It explodes.
The energy of a supernova explosion is essentially equal to all of the energy that the sun will put out in its 10 billion year lifetime. And yet the supernova delivers this in less than a day and then expands for a few months afterwards. As it expands, it's as bright as an entire galaxy. It's as bright as a billion suns.
Extreme nuclear processes within the dying star fuse the elements the star created in life to make heavier elements. As the star explodes, it blasts these into space.
In its death, it creates the essential elements for making planets and life elsewhere. It spews the products of millions of years of nuclear reactions out into the gas in between the stars.
This is the basis for some of the clouds that eventually form new stars. Yet they're spread so thin that it's difficult to know what triggers a cloud like this to collapse. The best way to find out is to examine the material that once made up the cloud. And that means examining the two oldest types of material in the solar system: asteroids and comets. But first, scientists need to bring back a sample from outer space. Comets are relics from the earliest days of the solar system and may hold clues to our origins. But before scientists could study them in depth, they needed samples. In 1981, this man, NASA's Dr. Peter So, started to work on his idea to return comet fragments to Earth.
It's almost like space forensics. It's like you see some television program, a crime scene, they find a piece of paint chip or a hair or some kind. Very similar to what we're trying to do.
So and his colleagues designed the Stardust Probe to travel around 500 million kilometers from the Earth and collect comet grains from the comet Wild 2. There's just one problem. The dust particles will be moving up to 6 times faster than the speed of a bullet. Yet it's vital So gets them back to Earth undamaged.
So what I need is special material to be able to contain the high-speed bullet. I'd be able to capture it without breaking up. So I need to capture the bullet without breaking out the bullet.
It takes So over 2,000 experiments to refine his comet-catching material. It's made of the same chemical as glass, silicon dioxide, only 1,000 times less dense. So calls it smooth gradient silica aerogel. If anything can stop comet grains, it's this stuff. With aerogel capture cells on board, the probe is good to launch. On February 7th, 1999, it blasts off on top of a Delta rocket.
We have main engine start and liftoff of the Stardust spacecraft, returning a time capsule with the elements of the formation of our solar system.
Its 3.2 billion kilometer journey takes nearly 5 years, but eventually the night of the comet encounter arrives. At Mission Control, all So and his colleagues can do is wait.
We have done many simulations, but still the questions, will it run into a comet? Even if it doesn't run into the comet, did it collect dust at all? It would be horrible when it comes back and no dust.
Finally, in 2006, the capsule re-enters Earth's atmosphere. It makes a safe landing, and scientists rush its precious cargo to the lab. As soon as they open it, they know the mission is a success.
If I capture one particle that I can see with the naked eye without a microscope, I will be pleased. But I caught more than 3 dozen of them.
It's an incredible achievement. These are the first pristine comet particles ever to return to Earth. The grains may be tiny, but they contain a wealth of information.
It will take many years really to understand the formation of the solar system. It will take probably a couple of decades to milk all we can from the Stardust samples.
The team may have to wait decades for all the results, but in the meantime, others are trying a different approach. Comets aren't the only source of material from the early solar system. Meteorites are ancient too, and they have one huge advantage. they come to us.
The amazing thing is that any time you pick up a meteorite, with very few exceptions, you take it into the laboratory, you date it, the answer is it's 4.5 billion years old. 4.5 billion years old. These are pieces of the early solar system. And so here you have in your hand a piece of something very substantial that connects you and connects our existence and connects the history that brought us to be with this larger universe.
After extensive analysis, Hester's team discover unstable isotopes of iron-60 locked inside the meteorites. It's totally unexpected. Iron-60 decays relatively quickly, so it must have come from close by. If it came from any great distance, it would have had time to decay into a different isotope before the meteorite could trap it. Only a supernova can make iron-60. So there must have been an active supernova close to the infant sun.
To come along with a piece of hard evidence that says that nope, early sun, early solar system, we're in a violent environment near a massive star, experienced a nearby supernova, it was surprising. We realized that this is going to change the way that people think about what goes on. This is going to change our understanding of the origins of the solar system.
Despite the violent forces being unleashed, our solar system may have formed right alongside a supernova.
These are exquisitely violent events, and they reshape everything around them.
Shockwaves from exploding supernovae pummel everything within 20 light-years. A galactic bomb blast. What's astonishing is that all that destructive force may have been exactly what was needed. Blast waves can push dispersed matter together, like a broom sweeping up dust. So the collapse of our giant cloud of dust may have been triggered by the blast from the nearby supernova.
They'll send shock waves and compress the gas for light years around them, and that compression triggers the birth of other stars.
The blast wave could have swept together the material of our nebula. When compressed enough, gravity would start to have an effect, and the cloud would begin to collapse. Within the cloud swirling about the infant sun, the planets are beginning to take shape. And today, scientists are beginning to understand the astonishing processes that formed them. For years, the process of planetary formation has puzzled scientists. Some astronomers now believe planets grow within the disk of gas particles surrounding a newborn sun. But this material is spread too thin for gravity to pull it into clumps. Then, in 2003, some informal experiments on board the International Space Station shed some light on this long-standing mystery. Astronaut Don Pettit spends his free time in space, conducting a few experiments to see how particles behave in zero gravity. He takes different grains such as coffee, sugar, and salt, places them in pouches, and watches as they begin to attach to each other. He realizes that the friction between them as they rub together inside the pouches is creating an electrostatic charge that pulls particles together and forms them into clumps. The same electrostatic charges would have been created if the experiment were carried out on Earth. But on Earth, the far stronger force of gravity would have made it impossible to observe the same results. Pettit and his colleagues realized that what they're seeing in the zero-gravity conditions of the space station would have also occurred in the zero-gravity environment of the early solar system. The particles in the protoplanetary disk may somehow get charged and attract each other. It's a process known to planetary scientists such as Jack Lissauer as accretion.
We see signs of accretion in our daily lives. Raindrops condensed as very, very tiny droplets around small little pieces of dust, and they collide with one another as they fall in much the same way that grains collide in the solar nebula and accrete into bigger objects.
Once the clumps reach the size of mountains, they exert a significant gravitational force. It's more powerful than the electrostatic force, so the whole process accelerates fast. In about 1 million years, the clumps can grow into larger planetesimals, or pieces of planets, and can keep on growing into full-size planets. Gravity keeps these planets locked into their orbits around the Sun. Traditionally understood as a mysterious pulling force, since Einstein, scientists have a new understanding of gravity.
Most people know that it's the sun's gravity that keeps planets moving in orbits around the sun. What we're going to do here is we're going to take a little bit deeper look at what the nature of gravity really is. Now, Newton's first law of motion, law of inertia, says that an object moving in a straight line at a constant speed will keep doing so. So here in the overhead view, we're looking down at a flat surface, and if I take this ball, which represents a planet, and I roll it across the surface, sure enough, it moves in a straight line at a constant speed. Now, Einstein said there's actually more to it than that. Einstein said that if you took a mass, for example, the mass of the sun, represented here by this plunger, that mass had the effect of distorting the shape of space-time. Now, to us, it doesn't look distorted. If you look on the overhead shot, it still looks as flat as it did before, just like a chessboard, but in fact, it is distorted. And so now when I take my planet and I move it through this distorted space-time, it tries to follow a straight line, but there's no straight line available for it to follow. And so instead what it winds up doing is it winds up moving around the central object on an orbit. It's that effect of that curved space-time that we usually call gravity.
Gravity exerts an equal force in every direction, so its effect is always to attract matter evenly towards the center of a body. Therefore, when it's strong enough, gravity will re-sculpt any body into a sphere. This is why all planets in the solar system form nearly perfect spheres. With a diameter of over 480 kilometers, no other shape is possible. All the planets are roughly spherical, and all come from the same original disk. But they all end up as radically different worlds, from rocky Mars to gassy Jupiter. The differences are primarily down to one basic law of physics. Different kinds of material condense at different temperatures.
It has to do with, given a given temperature, what is a gas and what is a solid, and that's it.
At first, all the matter around our young star is so hot it's in a gaseous form. Then further out, as things cool, material begins to condense out of the cloud, like snowflakes forming on Earth. In the inner solar system closest to the Sun, it stays hot, far too hot for gases or ices to condense. At these temperatures, they'd evaporate instantly. But metallic particles can condense here, and the planet that forms in this zone is highly metallic Mercury. Astrophysicist Steve Desch is an authority on planetary formation. His research has shown him just how hostile a world Mercury must be.
It has no atmosphere, it has no oceans, it's just rock. And the part that faces the sun tends to get hot enough to melt lead, for example. It's many hundreds of degrees Fahrenheit.
The fierce heat is thanks to Mercury's proximity to the sun. It's almost 3 times closer than the Earth. Move further out and the temperature eases a little, by around 500 degrees Celsius. Now more rocky particles can condense, so the rockier terrestrial planets, Venus, Earth and Mars, form in this region. Since Venus orbits around 50 million kilometers further from the Sun than Mercury, we could expect it to be a more hospitable place.
Venus is probably the closest thing we have in the solar system to your conception of hell. The pressures are immense, the temperatures are high, and it rains sulfuric acid.
Around 40 million kilometers further, our home planet.
The Earth has been nicknamed the Goldilocks planet. It's not too hot, it's not too cold. It's orbiting at just the right distance from the Sun, and that makes it very conducive to life.
Earth has a protective ozone layer to shield us from harmful UV radiation, and a magnetic field that deflects lethal cosmic radiation. Earth is also the only inner planet to have a large moon. Today, scientists like Gary Lofgren still study the lunar samples first brought back by the Apollo astronauts over 30 years ago. Lofgren works in the secure lunar storage facility, where NASA keeps most of the 380 kilos of rock brought back from the moon. For years now, scientists have been studying the samples to discover how the moon and the wider solar system may have been formed. It's an invaluable resource for geologists, and the Apollo astronauts made it a top priority to bring samples back, even if it meant ignoring orders.
Neil Armstrong personally made sure that we got a bunch of rocks by basically sort of disobeying the rules, as I understand it, and he kind of snuck out of the view of the TV camera, which he wasn't supposed to do, and filled up a box full of rocks.
When the samples are analyzed back in the lab, they soon give up some surprising information.
We found out quickly that the chemistry was very different from the Earth, and it wasn't the kind of chemistry we expected from our previous ideas about the formation of the moon.
The lunar rocks, and therefore the moon itself, turn out to be younger than previously thought.
All the theories we thought of before we went there kind of went out the window really quick, and it took a few years before good ideas began to come forth.
According to nebular theory, there should not be enough of the right material left over from planetary formation for moons to form in the inner solar system. It remained a scientific conundrum until, after decades of painstaking work, scientists came up with a new theory, a violent and devastating scenario that involved the Earth experiencing a head-on interplanetary smash. In 1969, Neil Armstrong becomes the first man to walk on the moon. Only when the Apollo astronauts bring back lunar samples are scientists finally able to understand how our moon may have formed. Their study of chemical isotopes in the samples suggests the moon contains material that was once part of the Earth. It is a totally unexpected find. Scientists are at a loss to explain how this material got there. But eventually, a bold new theory emerges. A theory suggesting that in the early solar system, there were not 8, but around 20 planet-sized objects orbiting the Sun.
When you think about the early stages of planet formation, you can think of it as a sort of a pinball game where there are these objects that are careening all over the place, occasionally running into one another.
4.53 billion years ago, the young Earth is on a direct collision course with an object named Theia, a body the size of Mars.
If we had that collision today, it would probably be the end of mankind. It would be the equivalent of many, many hydrogen bombs exploding on the surface of the Earth.
It's a world-shattering impact, blasting material with such force that billions of tons of rock escape Earth's gravity and eject into space. This material is captured by the Earth's gravitational pull and enters into orbit. Over a few million years, it amalgamates and becomes our moon. The collision is further evidence of a violent early solar system, a period when countless bodies followed chaotic orbits. Often they'd wreak havoc, but some objects became permanent features of our system. The two Martian satellites, for example, Phobos and Deimos, are both believed to be former asteroids captured by the gravity of Mars. These two moons are relatively tiny. Even the larger body, Phobos, is just 1/10 the size of our moon. Although Mars itself is only 1/3 the size of Earth, it has some of the most extraordinary features in the solar system.
Mars is a spectacular planet, a geologist's wonderland. For example, it has the solar system's largest canyon, Valles Marineris, which has side tributaries which would dwarf the Grand Canyon on Earth. It's about the length of the United States. It has the solar system's largest volcano, Olympus Mons, which would dwarf Everest.
Mars is the last of the 4 inner terrestrial planets, the rocky bodies orbiting inside the asteroid belt. That these planets stopped growing at their present-day size was largely down to the question of supply. Rock and metal were scarce in the early solar system, making up only around 0.6% of the total material available. Also, the inner planets couldn't accumulate gas compounds because it was too hot for them to condense here. All of the gas compounds condense much further out. Before we reach this zone and the outer planets, there's the asteroid belt to contend with. Science fiction paints this as a crowded zone difficult to cross.
We now know that there are at least tens of thousands of asteroids in the asteroid belt that are a mile or larger in size. Nevertheless, it would be very unlikely if you were piloting your spaceship through the asteroid belt to run into one of these. In fact, we have to aim very carefully to get space probes to visit asteroids. The average distance between asteroids in the asteroid belt is about 1 million miles.
As we traverse the asteroid belt, we hit an invisible but critical border. It's called the frost line. Cross this boundary in space, around 450 kilometers out from the Sun, and we find totally different kinds of planets.
There was a frost line somewhere in the asteroid belt, beyond which it was cold enough for water to condense. And this was a gradual transition, but a very important one.
Beyond the frost line, the outer planets take shape. These are very different worlds to the inner planets, and that's due to the kinds of substance that can condense in this cooler region. Colder than -70 degrees Celsius, hydrogen compounds like water, methane, and ammonia are able to condense. And there are trillions of tons of this material available in the early solar system. But it's only once the outer planets reach 10 times the mass of Earth that their growth really takes off. At that critical mass, they have enough gravitational influence to start sucking up trillions of tons of gas. There's a snowball effect. As they get bigger, the planets attract ever more gas.
It was a race about how fast these cores could grow compared to how long the gas disks hung around. Jupiter and Saturn just happened to be at the right place in the solar system.
They quickly become gigantic superplanets. And since gas now makes up 90% of their mass, they're also known as the gas giants. Largest by far is Jupiter. This giant planet has a mass of over 300 times that of Earth, while its volume is more than 1,000 times greater. According to Hal Leveson, we're fortunate that Jupiter did reach this size. The planet's gravity is so powerful, it often changes the trajectory of comets that could otherwise enter the inner solar system.
Jupiter actually plays the role of a protective big brother that protects us from the hostile environment that exists beyond its orbit. And in particular, there are a lot of these small icy comets that could come in and hit us, that Jupiter deflects away, throwing them out of the solar system.
Saturn is the second largest planet in the solar system. It turns out we're lucky it never got any bigger.
According to our simulations, if you have two planets the size of Jupiter in one solar system, they will eventually knock out all the other planets. Now, we were close. Saturn is not that much smaller than Jupiter, so we were right on the border of being a stable solar system. Had Saturn been a little bit bigger, we probably wouldn't be here talking about it.
It's a terrifying thought. The gravity of a larger Saturn acting in concert with Jupiter could have sucked in and destroyed all the smaller planets. Thankfully, Saturn never follows this fateful path. Instead, it grows into one of the crowning glories of our solar system.
Whenever I show people planets in my telescope, I always save Saturn for last. It's beautiful, it's so stunning. It's definitely a gorgeous planet because of its large rings.
The rings are made up of billions of fragments. These fragments continually grow and disintegrate due to the conflicting gravitational forces of Saturn and its moons. Uranus lies nearly twice as far out from the Sun as Saturn. Both it and Neptune are icy worlds, with much less gas than the other gas giants.
In a sense, they got to the feast too late.
Uranus is a plain-looking place. A flat green color thanks to a layer of methane high in its atmosphere. Since it forms further out, it becomes an ice giant rather than a gas giant. Temperatures average minus 212 degrees Celsius. Since Pluto has been officially downgraded to dwarf planet status, Blue Neptune is now our outermost planet. Until recently, these bodies were thought to mark the very edge of our solar system.
Our idea of the solar system changed drastically, really, in 1992 when this structure that we call the Kuiper Belt today was discovered.
Around 45 billion kilometers out from the Sun, the Kuiper Belt, home to an estimated 70,000 large, icy objects.
There's a whole population of leftover dregs of planets formation, you can think of it as, right, where these things haven't quite come together.
Then, 1,000 times more distant from the Sun, lies the mysterious Oort cloud, comprised of up to 1 trillion comets. Most of these probably formed much closer to the Sun as part of the same process that formed the planets. But the gravitational influence of the young Jupiter and Saturn forced most of these comets onto very long orbits, carrying them to the far reaches of the solar system. The outer edges of the Oort cloud really are the final frontiers, almost a full light year out from the Sun. Beyond our solar system lie billions of other stars, many with planets of their own.
For a long time, it's been one of the holy grails of astronomy to actually find a planet around another star. The only solar system, the only planets we knew about were our own. So what was the first planet going to be like around another star?
Then in 1992 comes the discovery they've been waiting for. The first ever detection of an exosolar planet. A planet orbiting a distant star.
And then the very first planet we find outside our solar system is bigger than Jupiter, way up against the star. It completely threw out everything that we'd been taught about solar systems.
There is absolutely no way that an object that big could form close to their star. There's just not enough stuff there.
The nature of these planets simply doesn't fit within standard models of solar system formation. And it's not just a problem for distant worlds. When we look back at our own solar system, it becomes clear there are problems with the standard theory of how our planets formed.
It's interesting, when we try to apply our models, our understanding of planet formation, to Uranus and Neptune, they fail utterly. You just can't build those planets where we see them today.
There simply should not have been enough material available at this distance from the Sun for planets this size to grow. It's a mystery. Uranus and Neptune seem to be in the wrong place. And this is just one of several mysteries that standard nebula theory cannot explain. There's also the enigma of the Kuiper Belt. According to the model, it shouldn't really be there. Even more puzzling, our moon's craters all seem to date from the same time. Together, these problems threaten to undermine scientific understanding of how the solar system forms. The moon may be our closest neighbor, but it still harbors secrets. With no substantial atmosphere or weather, the lunar landscape experiences little change. So it was believed that one impact strike every few thousand years would be enough to explain its cratered surface. But then the Apollo missions brought back lunar rock samples, including cratered debris thrown out by ancient impacts. And these samples tell a very different story.
It became clear as we studied the moon that a large number of the impact craters formed around 3.9 billion years ago. And clearly there was a high concentration of impacts on the moon during that time.
Lunar geologists use radiometric dating to assess the age of the samples. It came as a big surprise to find out that a high proportion of moon craters formed during one relatively brief period of bombardment. Dr. David Kring is an expert on this phase, known as the Late Heavy Bombardment, or lunar cataclysm.
This evidence from the moon is actually telling us something about the entire origin and architecture of the solar system and how it evolved.
Tens of thousands of large meteorites must have hit the moon during the lunar cataclysm. Earth, too, must have taken a pounding. Today, only younger craters, like this 20,000 to 50,000-year-old example in Arizona, remain on Earth. Most older craters have disappeared, but 3.5 billion years back, there'd been no chance of missing them.
We're talking about 20 to 40,000 impact craters that would have had enough energy to change global conditions.
Where could such a vast number of impact objects come from?
Within the impact craters, we have chemical traces of the objects that produce them, and those point to the asteroid belt.
It seems to match. The objects that once hit the moon are chemically consistent with the rocks found in the asteroid belt. So this is almost certainly where they came from. But today, most asteroids are in stable orbits. There's nothing obvious that could force thousands of them out of the asteroid belt and into the inner solar system. So for decades, the bombardment was a scientific puzzle. In 2004, Hal Levinson had a eureka moment. Working with an international team, he came up with a new model of solar system formation.
It's like a light going off. You sit in your office and you say, I've solved this problem people have been working on for decades, and I'm the only one in human history that understands this little part of the problem we're trying to solve.
Levinson's idea assumes that the planets might have formed in very different orbits and then moved. Most scientists had believed the solar system was stable and relatively predictable, but many experts now believe this is totally wrong.
This flies in the face of conventional wisdom. Astronomers probably always thought the planets formed where we find them today. These new numerical simulations, which show that they migrated a substantial amount and even had close encounters that caused them to switch their order, is startling and new.
In Levinson's simulations, Jupiter and Saturn tugged on each other whenever their orbits came closest together, but overall these pulls cancelled out. Only when Jupiter circled the Sun exactly twice, for every time Saturn circled once, did something dramatic seem to occur. It's called a 2-to-1 resonance, and it happened 3.9 billion years ago.
And that configuration actually makes the planets jiggle with one another. They perturb one another.
Instead of cancelling out, the two planets' gravitational tugs then work in the same direction. To Levinson, it's just like pushing a swing. Each well-timed push nudges the swing higher. For Jupiter and Saturn, each gravitational nudge stretched their orbits until they reached their present-day patterns. But the process had a fateful impact on other planets.
Uranus and Neptune can't stand that at all, and they just go totally bonkers. The orbits cross one another, they gravitationally get close to one another. One of them gets thrown out, the other one gets thrown in. They rattle around off the Jupiter and Saturn.
According to the theory, Uranus and Neptune may even switch places, ripping surrounding swarms of asteroids out of their orbits. It's a recipe for disaster. Some asteroids are thrown out into space, while others are pushed into the sun. Thousands slam into the inner planets and Earth's moon. It sounds like an improbably chaotic transformation, but the evidence now suggests this did happen. It could never happen today. Jupiter and Saturn are now too far apart, but this event may have been a key moment in the formation of our solar system. But the really incredible thing is that it could so easily have turned out very, very different.
You could have the wrong type of star. You could have too many giant planets. There are many ways things can go wrong. And we're right there on that thin, lucky line of existence.
Instead of the diverse solar system we now see, we could have remained forever as ashes, gas, and dust. And what of our future? 5 billion years from now, as our sun runs out of fuel, it will expand, consuming some of the inner planets. Other planets may survive as ghost worlds, still orbiting their dead sun. There will be no life of any kind. But for now, we're lucky to be alive.